In the stillness of nothingness, before the birth of time itself, there was a vast and infinite expanse, a realm where silence reigned supreme. This was not the silence of an empty room, but a deeper, more profound quiet, a silence that was both absolute and eternal, stretching beyond the boundaries of imagination. There was no light, no darkness, no up, no down, only the quiet void, endless and unchanging. In this timeless void, there was no past, no future, only an eternal present, a moment frozen in the fabric of the cosmos, waiting to be unfurled. It was a space without dimensions, where the concept of existence itself was yet to be defined. There was no matter, no energy, no life, just the potential for all that would come to be. The universe as we know it was not yet born, but the seeds of creation were there, waiting in silent anticipation. In this infinite void, the first whispers of existence began to stir, like a faint breeze rustling through the leaves of a tree. It was a presence, subtle and almost imperceptible, but it carried within it the promise of everything that was to come. This presence was the precursor to the universe, the very essence of creation itself, and it was on the brink of awakening. The cosmos was poised at the edge of a great transformation, a moment of profound change that would give birth to everything we know, the stars, the planets, the galaxies, and all the life that would eventually spring forth. But at this moment, all was still, as if the universe was holding its breath, waiting for the signal to begin. In this tranquil state, time itself had no meaning. There was no beginning or end, just the infinite potential of what could be. The void, though empty, was not devoid of purpose. It was the canvas upon which the masterpiece of creation would soon be painted, a canvas as vast as it was empty, stretching beyond the furthest reaches of imagination. And then, in the quiet of this timeless void, something miraculous happened. The first tremors of existence rippled through the fabric of the cosmos, subtle at first, like the softest of whispers, but growing in strength and intensity. These were not tremors of destruction, but of creation, the gentle stirring of a universe about to be born. The potential that had lain dormant for an eternity was now awakening, slowly but surely, like a flower opening its petals to the warmth of the sun. The void, once silent and still, began to hum with the quiet energy of creation, a low, soothing vibration that resonated through the very fabric of existence. It was the first sign of life in a universe that had not yet begun, a precursor to the wonders that were about to unfold. This was the beginning of everything, the moment before the Big Bang, when all the matter and energy that would ever exist were compressed into a single, infinitesimally small point. It was a moment of pure potential, where every star, every planet, every atom was contained within a space no larger than a grain of sand. But within that tiny point, the future of the universe was already written, waiting to be unleashed in a burst of creation that would shape the cosmos for billions of years to come. The universe, now stirred from its primordial slumber, was poised to undergo a transformation of unimaginable scale. The tranquil void that had existed before was about to give way to a new era, a time of creation where all that ever was and all that ever will be would burst forth in a symphony of light and matter. This moment, known to us as the Big Bang, was not a violent explosion, but a serene, inevitable unfolding of the universe's potential. In a moment that lasted but a fraction of a second, this singularity began to expand. The universe did not explode outward with destructive force, but rather it expanded smoothly, like a balloon inflating in the gentle embrace of the void. This was the birth of time and space, the first seconds of a cosmic journey that would continue for billions of years. As the universe expanded, it began to cool. The intense heat of the initial moment began to dissipate, and the first particles of matter emerged from the primordial energy. These were the building blocks of everything that would follow, quarks and gluons, which would soon combine to form protons and neutrons. This was the first step in the creation of the universe, a peaceful gathering of fundamental particles into more complex forms. The universe, still in its infancy, was a sea of radiant energy and nascent matter. Photons, the particles of light, streamed through the early cosmos, illuminating the darkness for the first time. This light, though dim and diffuse, was the first glimmer of the stars that would one day fill the sky. As the universe continued to expand and cool, the quarks and gluons bonded to form the first protons and neutrons. These particles, in turn, began to combine, forming the nuclei of hydrogen and helium, the lightest and most abundant elements in the universe. This process was a quiet, steady progression, as the universe methodically laid the groundwork for the galaxies, stars, and planets that would come. The universe was still young, only seconds old, but it was already full of potential. The first atoms had not yet formed, but the seeds of everything were there, waiting for the right conditions to emerge. The cosmos was a place of gentle transformation, where energy became matter, and matter began to take on the forms that would define the universe. During this time, the universe was also undergoing a period of rapid expansion known as inflation. In the blink of an eye, the universe grew from the size of a subatomic particle to a size comparable to a grapefruit. This expansion smoothed out any irregularities, creating a uniform cosmos that would later give rise to the galaxies and clusters we observe today. It was as if the universe, in its infancy, was preparing a vast canvas on which the masterpiece of creation would be painted. As inflation slowed and the universe continued to cool, the particles that had formed in the first moments began to interact more freely. Electrons, which had been zipping through the early universe, began to slow down, drawn to the positively charged protons. This union would eventually form the first atoms, but for now, the universe remained a hot, dense plasma where particles and light were tightly coupled. The early universe was a place of delicate balance, where the forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, began to shape the cosmos. These forces worked in harmony, guiding the formation of the first structures in the universe. It was a time of quiet collaboration, as the fundamental forces of nature worked together to build the universe from the ground up. And so the universe continued to expand, its journey just beginning. The Big Bang was not a single event, but the start of a long, slow unfolding of creation. Each moment brought new wonders, as the universe methodically built itself from the simplest particles to the most complex structures. The birth of the universe was a peaceful, orderly process, one that would continue for billions of years, shaping the cosmos into the magnificent tapestry we see today. As the universe continued to expand and cool after the Big Bang, it entered a new phase in its development, a period where the building blocks of matter began to take shape. The first moments of creation had given birth to the simplest particles, but now, in the quieter aftermath, these particles would combine to form the atoms and elements that would serve as the foundation for everything to come. In the earliest seconds after the Big Bang, the universe was a hot, dense sea of energy and particles. Quarks and gluons, the most fundamental constituents of matter, moved freely in this chaotic environment. But as the universe expanded, it began to cool, and these quarks and gluons started to coalesce into protons and neutrons, the building blocks of atomic nuclei. The formation of protons and neutrons was a delicate process, governed by the forces of nature in a perfect balance. As the temperature continued to drop, these protons and neutrons began to combine in pairs and small clusters, forming the first atomic nuclei. This process, known as nucleosynthesis, occurred just minutes after the Big Bang and was responsible for creating the first elements: hydrogen, helium, and trace amounts of lithium. These early nuclei floated freely in the expanding universe, surrounded by a sea of electrons. However, it would take much longer, around 380,000 years, before the universe cooled enough for these electrons to slow down and bind with the nuclei, forming the first neutral atoms. This was the era of recombination, a peaceful and gradual process that transformed the universe from a hot, opaque plasma into a transparent cosmos filled with the first atoms. Hydrogen, the simplest and most abundant element, was the first to form. Each hydrogen atom was composed of a single proton in its nucleus, orbited by a lone electron. This element would become the most important building block of the universe, providing the fuel for the first stars and playing a central role in the formation of galaxies. Helium, the second most abundant element, was also formed during this time. Its nucleus, composed of 2 protons and 2 neutrons, made it more stable and slightly heavier than hydrogen. Helium atoms, with their 2 electrons, were among the first to combine in the early universe, adding to the growing richness of the cosmos. These simple atoms, though small, were the seeds from which all complexity in the universe would grow. They drifted through the expanding universe, carried on the gentle currents of space-time, gradually gathering into clouds of gas that would eventually form the first stars. The formation of these atoms was a quiet, methodical process, one that laid the groundwork for the creation of more complex elements, and eventually the rich diversity of matter that we see in the universe today. As the universe continued to cool and expand, these primordial atoms began to clump together under the influence of gravity, forming vast clouds of gas. Within these clouds, the conditions were just right for the first stars to ignite, and with them, the first steps toward the creation of heavier elements. The process of stellar nucleosynthesis, where stars fuse lighter elements into heavier ones, would later give rise to the diversity of elements found throughout the cosmos. The universe was now a place of quiet beginnings, where the simplest elements were taking their first steps toward forming the complex structures that would define the cosmos. The formation of atoms was just the beginning, a peaceful prelude to the grand symphony of creation that was about to unfold. The stage was set for the formation of stars, galaxies, and ultimately the planets and life that would come to inhabit the universe. In this era of formation, the universe was still young, its future full of possibility. The atoms and elements that had formed in these early moments would go on to play a crucial role in the development of everything we see around us today. From the smallest grain of dust to the largest galaxy, everything traces its origins back to this quiet, deliberate process of creation, a process that began with the simplest elements in the aftermath of the Big Bang. As the universe continued its steady expansion, the atoms that had formed in the early moments began to gather into vast clouds of gas, setting the stage for one of the most fundamental processes in the cosmos, the formation of stars. These stars would become the engines of creation, forging the elements necessary for planets, life, and the complex structures that make up the universe. In the cold depths of space, where the temperature had dropped significantly since the fiery moments of the Big Bang, gravity began to exert its quiet influence. Hydrogen and helium, the most abundant elements, started to clump together under this invisible force, forming immense clouds of gas known as nebulae. These nebulae were the nurseries of stars, regions where the raw materials of the universe were slowly coming together. Over time, these clouds of gas grew denser as gravity continued to pull more and more material into their embrace. The pressure at the core of these gas clouds increased, causing the temperature to rise. This process was slow and steady, taking millions of years, but eventually the conditions at the heart of these nebulae became just right for a remarkable transformation. As the temperature and pressure at the core of these gas clouds reached critical levels, nuclear fusion began. Hydrogen atoms, under the intense pressure of gravity, collided with such force that they fused together to form helium, releasing vast amounts of energy in the process. This energy, in the form of light and heat, marked the birth of a new star. The first stars, massive and luminous, ignited across the universe, their light piercing the darkness and filling the cosmos with a warm, steady glow. These stars were not just points of light, they were the first sources of energy capable of driving the processes that would lead to the formation of more complex elements, and, eventually, life. These early stars, known as Population 3 stars, were composed almost entirely of hydrogen and helium, the lightest elements created in the Big Bang. Because they lacked heavier elements, these stars were much larger and hotter than the stars we see today. They burned their fuel quickly, living fast and dying young, often in spectacular supernova explosions. These supernovae were more than just the violent deaths of stars. They were also the crucibles in which heavier elements were forged. In the intense heat and pressure of a supernova, lighter elements like hydrogen and helium were fused into heavier elements such as carbon, oxygen, and iron. These newly formed elements were then scattered into space, enriching the surrounding regions with the building blocks of planets and life. The remnants of these first stars mixed with the gas and dust of the universe, forming new generations of stars that were richer in elements than their predecessors. Each new generation of stars added more complexity to the universe, gradually building up the diversity of elements needed for the formation of planets, moons, and eventually life. The formation of stars set the stage for an even grander development, the birth of galaxies. These immense structures, composed of billions of stars, gas, dust, and dark matter, would become the defining features of the universe, shaping its overall structure and influencing the formation of planets, stars, and life itself. In the early universe, the distribution of matter was not perfectly uniform. Small fluctuations in density, remnants from the chaotic moments following the Big Bang, created tiny overdensities where matter began to clump together under the influence of gravity. These overdensities were the seeds from which galaxies would grow. Over millions of years, these regions of higher density attracted more and more matter, gradually forming large clouds of gas and dark matter. As these clouds collapsed under their own gravity, they began to rotate, spinning faster and faster as they drew in more material. This rotation caused the gas within these clouds to flatten into disc-like shapes, a process that would ultimately lead to the formation of spiral galaxies, like our own Milky Way. Within these rotating disks, the conditions were ripe for the formation of stars. As the gas and dust continued to collapse, pockets of material within the disks grew dense enough to ignite nuclear fusion, giving birth to new stars. These stars began to group together, forming the bright clusters that would become the core regions of galaxies. The formation of these stars was a continuous process, with new stars forming and older ones burning out over millions of years. The interplay between gravity, gas, and dark matter in these early galaxies was a delicate balance. Dark matter, which does not interact with light but exerts a gravitational pull, played a crucial role in the formation of galaxies. It acted as a scaffold, providing the necessary mass to hold galaxies together and influence their shapes. The exact nature of dark matter remains one of the great mysteries of modern cosmology, but its presence was essential for the birth and evolution of galaxies. As these nascent galaxies continued to evolve, they began to take on the diverse forms we see today. Some, like the Milky Way, formed into spiral galaxies, with their distinctive arms of stars and gas spiraling outward from a central bulge. Others formed into elliptical galaxies, which are more spherical or oval in shape and contain older, more evolved stars. Still, others became irregular galaxies with no defined shape, often the result of gravitational interactions or collisions with other galaxies. Galaxies did not form in isolation. As they grew and evolved, they began to interact with one another, sometimes merging to form larger galaxies or colliding in spectacular events that triggered bursts of star formation. These interactions played a significant role in shaping the structure of the universe, creating vast clusters and superclusters of galaxies connected by filaments of dark matter and gas. The birth of galaxies marked a crucial phase in the evolution of the universe. These immense structures not only housed the stars that would light up the cosmos, but also served as the cradles for planetary systems and, ultimately, life. The formation of galaxies was a gradual and ongoing process, one that continues to this day as new stars and galaxies are born, even as others reach the end of their life cycles. As the universe expanded, galaxies began to move apart, carried by the expansion of space itself. This movement created the large-scale structure of the universe, with galaxies clustered together in groups and superclusters, separated by vast voids of empty space. The distribution of galaxies across the universe is not random, but follows a complex web-like pattern known as the cosmic web, shaped by the interplay of dark matter, gravity, and the expansion of the universe. The birth of galaxies was a turning point in the history of the cosmos. These vast collections of stars and matter provided the environments necessary for the formation of planets and, eventually, the emergence of life. The universe, once a simple and homogeneous expanse, had now become a complex and dynamic tapestry of galaxies, each one a microcosm of creation, destruction, and evolution. As the galaxies continued to evolve, they would go on to play a central role in the ongoing story of the universe. From the formation of stars and planets to the emergence of life, galaxies were the stage upon which the drama of the cosmos would unfold. The birth of galaxies was not just an event in the distant past, but a continuing process, one that shapes the universe we see today and will continue to influence its evolution for billions of years to come. As the galaxies continued to evolve, they became the building blocks of the large-scale structure of the universe. Each galaxy, a vast collection of stars, planets, gas, dust, and dark matter, contributed to the grand cosmic tapestry that stretched across the universe. The galaxies were not evenly distributed. Instead, they clustered together, forming groups, clusters, and superclusters, all interconnected by vast filaments of dark matter and gas. These structures, known as the cosmic web, are the largest known formations in the universe. The cosmic web is a complex network of interconnected galaxies stretching across billions of light years. It is within this web that galaxies interact with one another, sometimes merging to form even larger galaxies, and other times colliding in dramatic events that trigger bursts of star formation and reshape the galaxies involved. The process of galaxy formation and evolution is influenced by a variety of factors, including the initial conditions of the universe, the distribution of dark matter, and the interactions between galaxies. Gravity plays a central role in this process, pulling galaxies towards one another and driving the formation of clusters and superclusters. These structures are held together by the gravitational pull of dark matter, which makes up the majority of the mass in the universe. Within the cosmic web, galaxies are constantly evolving. They form new stars from the gas and dust within them, and as these stars age and die, they enrich the surrounding environment with the heavier elements forged in their cores. These elements, scattered into space by supernovae and stellar winds, are the building blocks for future generations of stars and planets. As galaxies evolve, they also undergo a variety of interactions with one another. Some galaxies pass close enough to each other to be gravitationally influenced, leading to the exchange of stars and gas. In some cases, galaxies may merge entirely, forming a single, larger galaxy. These mergers are often violent events, causing dramatic changes in the structure and appearance of the galaxies involved. The resulting galaxy may take on a new shape, with its stars, gas, and dust rearranged by the gravitational forces at play. These interactions and mergers are a key part of the ongoing evolution of the universe. They help to shape the galaxies we see today, influencing their sizes, shapes, and star formation rates. Over billions of years, these processes have created the diverse array of galaxies that populate the universe, from the spiral galaxies with their graceful arms of stars and gas, to the elliptical galaxies that are home to older, more evolved stars. Eventually, this led the way to the creation of planets. These celestial bodies, formed from the remnants of star formation, would become the diverse worlds that populate galaxies, each with its own unique characteristics and potential for life. The process of planet formation began in the dense clouds of gas and dust that surrounded newly formed stars. These clouds, known as protoplanetary disks, were the leftover material from the star's birth, and within these disks, the building blocks of planets were slowly coming together. The gas and dust in these disks began to collide and stick together, forming larger and larger particles. Over time, these particles coalesced into planetesimals, small solid bodies that would eventually become the cores of planets. As these planetesimals grew larger, their gravity began to attract more material, allowing them to grow even further. Some of these planetesimals collided and merged, forming larger protoplanets, while others were ejected from the disk or destroyed in collisions. The process of planet formation was chaotic and violent, with countless collisions and mergers shaping the final planetary systems. As protoplanets continued to grow, they began to clear their orbits of debris, sweeping up smaller planetesimals and gas. The most massive protoplanets could attract and hold onto thick atmospheres of gas, becoming gas giants like Jupiter and Saturn. Others, unable to retain such atmospheres, became rocky terrestrial planets like Earth and Mars. The composition of a planet depended on its distance from the parent star. In the inner regions of the protoplanetary disk, where temperatures were higher, only materials with high melting points, such as metals and silicates, could condense and form solid bodies. This led to the formation of rocky planets with solid surfaces. In the outer regions of the disk, where temperatures were lower, volatile compounds like water, ammonia, and methane could also condense, leading to the formation of gas giants and icy bodies. The formation of planets was not a uniform process. Different regions of the universe saw the formation of different types of planets, leading to a rich diversity of celestial objects. Some systems had multiple gas giants, while others were dominated by rocky terrestrial planets. Some planets formed in stable orbits, while others were ejected from their systems, becoming rogue planets drifting through interstellar space. As planets formed, they continued to evolve under the influence of their parent stars and the gravitational interactions with other planets in their system. Some planets experienced intense volcanic activity, shaping their surfaces and atmospheres, while others remained geologically inactive. The atmospheres of planets were also shaped by their interactions with the star, with solar radiation and stellar winds playing crucial roles in determining their composition and stability. The creation of planets was a complex and dynamic process, one that led to the formation of a wide variety of worlds. Some planets developed thick atmospheres, oceans, and the potential for life, while others remained barren and inhospitable. The diversity of planets in the universe is a testament to the complexity of the processes that shaped them, and each planet tells a unique story of its formation and evolution. As the planets continued to evolve, some developed the conditions necessary for life. On Earth, for example, the presence of liquid water, a stable climate, and a protective atmosphere allowed life to emerge and thrive. The formation of life on Earth was a delicate balance of conditions, and it is a balance that may have been achieved on other planets in the universe as well. The creation of planets was a fundamental step in the evolution of the universe, one that set the stage for the development of life and the continued evolution of the cosmos. The planets that formed in the aftermath of star formation became the environments where the chemistry of life could unfold, and they continued to play a crucial role in the ongoing story of the universe. The diversity of planets in the universe reflects the diversity of the processes that created them. From rocky terrestrial planets to gas giants, from icy moons to ocean worlds, the planets of the universe are as varied as the stars themselves. Each planet is a unique product of its environment, shaped by the conditions in which it formed and the forces that continue to influence it. As we continue to explore our own solar system and discover exoplanets orbiting distant stars, we deepen our understanding of the processes that shape these worlds. The study of planets, both near and far, offers insights into the history of our own planet and the potential for life elsewhere in the universe. The creation of planets is a story that continues to unfold, and as we look to the stars, we continue to learn more about the diverse worlds that populate the cosmos. In the early days of the solar system, the Earth was nothing more than a swirling mass of molten rock and gas, a chaotic collection of elements slowly coalescing under the influence of gravity. Over time, this fiery sphere began to cool and solidify, forming the first crust that would one day become the surface of our planet. This was a time of great turmoil, as meteorites and comets bombarded the young Earth, delivering water and other essential compounds that would set the stage for the emergence of life. As the Earth cooled, its surface began to take on a more stable form. The molten rock slowly solidified, creating vast plains of basalt and granite, the building blocks of the continents. Volcanic activity was rampant, with magma pushing its way to the surface, creating mountains and releasing gases that would eventually form the atmosphere. This was a time of constant change, but through it all, the Earth was slowly becoming more hospitable, more capable of supporting the delicate balance needed for life to thrive. The formation of the Earth's core was a crucial step in this process. As heavier elements like iron and nickel sank toward the center of the planet, they created a dense, molten core that generated a magnetic field. This magnetic field would become essential for protecting the Earth from the harmful radiation of the Sun, allowing the planet to retain its atmosphere and surface water. Above the core, the mantle churned slowly, driving the movement of tectonic plates that would eventually shape the continents and ocean basins. As millions of years passed, the Earth's surface continued to evolve. The once barren and rocky landscape began to change, with the first oceans forming as water vapor in the atmosphere condensed and fell as rain. These early oceans were vast and deep, covering much of the Earth's surface and creating a stable environment where the ingredients for life could mix and combine. The continents, meanwhile, began to drift apart and come together in a slow dance that would shape the face of the Earth for eons to come. The Earth's atmosphere, too, was undergoing a transformation. From its initial composition of toxic gases, it began to change, influenced by the chemical reactions taking place on the surface and in the oceans. Over time, this atmosphere would become rich in nitrogen and carbon dioxide, setting the stage for the development of a climate that could support life. The Earth, once a hostile and chaotic place, was slowly becoming a stable, life-supporting planet. As the Earth continued its transformation, the surface began to cool and solidify, giving rise to the first stable landmasses. These early continents were barren and lifeless, composed of jagged rocks and vast plains of basalt and granite. Yet, over millions of years, the relentless forces of erosion, wind, and water began to shape these landscapes, smoothing the rough edges and creating valleys, mountains, and plains. Beneath the surface, the Earth's interior remained dynamic, with the slow churning of the mantle driving the movement of tectonic plates. These plates, constantly shifting and colliding, shaped the Earth's surface, creating mountains, valleys, and ocean basins. Over time, the movement of these plates would lead to the formation of supercontinents, only to see them break apart again in a slow, inexorable cycle that continues to this day. The Earth's surface, once a chaotic and hostile place, was now a stable and life-supporting environment. The continents, oceans, and atmosphere had all reached a state of equilibrium, creating the conditions necessary for life to emerge. The planet, once a molten mass of rock and gas, had transformed into a blue and green oasis, teeming with the potential for life. The stage was set for the next great chapter in Earth's history, the birth of life itself. In the quiet stillness of the early Earth, life began to emerge in a process that was both delicate and profound. The planet, which had undergone such dramatic changes to become a stable, life-supporting world, was now ready to give rise to the first living organisms. It began in the oceans, where the conditions were just right for the complex chemical reactions that would lead to the formation of simple cells, the building blocks of all life. These first cells were incredibly simple, microscopic spheres that drifted in the warm, nutrient-rich waters. They were the pioneers of life, carrying within them the basic mechanisms that would allow them to grow, reproduce, and eventually evolve into more complex forms. For millions of years, these single-celled organisms were the only life forms on Earth, quietly multiplying and spreading across the planet's oceans. Over time, some of these cells began to develop new capabilities. Through a process of gradual change, they became more efficient at capturing energy from their environment, particularly from the sun. This led to the development of photosynthesis, a process that allowed these early organisms to harness the energy of sunlight and convert it into the chemical energy they needed to survive. This was a crucial step in the evolution of life, as it led to the production of oxygen, a gas that would eventually fill the Earth's atmosphere and make it possible for more complex life forms to develop. The emergence of life on Earth was a peaceful and gradual process, marked by small, incremental changes that, over vast stretches of time, led to the incredible diversity of life we see today. From these humble beginnings, life would eventually evolve into a myriad of forms, each one more complex and specialized than the last. But for now, in these early stages, life was simple, quiet, and unassuming, existing in harmony with the planet that had given it birth. As life continued to evolve on Earth, it did so at a slow and steady pace, filling the planet with a quiet diversity of forms. The oceans, which had once been barren and lifeless, were now teeming with a variety of simple organisms, each one adapted to its own unique niche. Some of these early life forms began to join together, forming colonies that worked together to survive. This was the first step toward multicellular life, a major milestone in the history of life on Earth. The evolution of multicellular organisms allowed for greater complexity, as different cells within the same organism could specialize in different functions. This led to the development of the first simple animals, soft-bodied creatures that moved slowly through the water, feeding on the abundant microorganisms that surrounded them. These early animals were the ancestors of all the complex life forms that would eventually come to dominate the planet, from the tiniest insects to the largest mammals. On land, life was also beginning to take hold, although it would be millions of years before plants and animals would fully colonize the continents. For now, the land was a quiet place, with only a few hardy microorganisms venturing out from the safety of the oceans. But even in this early stage, the groundwork was being laid for the eventual spread of life to every corner of the planet. The evolution of life on Earth was a gentle, unfolding process, one that was shaped by the forces of natural selection and the changing environment of the planet. Over billions of years, life adapted and diversified, filling every available niche with a wide variety of forms. Yet, through it all, the process remained quiet and steady, a testament to the resilience and adaptability of life. From the simplest cells to the most complex organisms, life on Earth has always been characterized by its ability to survive, thrive, and evolve in harmony with the world around it. In the vast reaches of our solar system, the planets move in a quiet, rhythmic dance, each following its own path around the sun. This cosmic ballet has been unfolding for billions of years, with the planets tracing their orbits in a silent harmony dictated by the forces of gravity. The sun, a glowing beacon at the center of this dance, holds each planet in its gravitational embrace, ensuring that they remain on their carefully choreographed paths. The inner planets, Mercury, Venus, Earth, and Mars, circle close to the sun, their rocky surfaces warmed by its radiant energy. These planets, with their solid surfaces and varied landscapes, have been shaped over eons by the gentle push and pull of gravity, as well as by the forces of erosion, volcanism, and tectonics. They move swiftly in their orbits, completing a full revolution in a matter of months or years, each one a unique world with its own story to tell. Beyond the rocky inner planets lie the gas giants, Jupiter, Saturn, Uranus, and Neptune. These massive planets, composed primarily of hydrogen and helium, move more slowly in their orbits, taking decades or even centuries to complete a single trip around the sun. Despite their great distance from the sun, these planets are still held firmly in its grasp, their orbits influenced by the same gravitational forces that guide the rest of the solar system. Each planet's orbit is an ellipse, a slightly elongated circle that keeps it at varying distances from the sun. This elliptical path is the result of the delicate balance between the gravitational pull of the sun and the planet's own inertia as it moves through space. This balance ensures that the planets remain in their orbits, neither spiraling into the sun nor drifting off into the cold depths of space. It is this balance that gives the solar system its stability, allowing life to flourish on Earth and ensuring that the planets continue their dance in the darkness of space. The dance of the planets is a quiet, timeless rhythm that has been playing out for eons, largely unnoticed by those of us on Earth. Yet it is this cosmic dance that has shaped our world, influencing everything from the length of our days to the changing of the seasons. The movements of the planets, though seemingly distant and abstract, have a direct impact on our lives, connecting us to the vastness of the universe in ways we may not always realize. As we gaze up at the night sky, the planets appear as tiny points of light, slowly moving against the backdrop of stars. These lights are the visible manifestations of a much larger, more complex system, a system that has been in motion since the birth of the solar system. The dance of the planets is a reminder of the order and harmony that exists in the universe, a silent testament to the power of gravity and the natural laws that govern all things. The dance of the planets is not just a solitary movement, but a complex interplay of forces that keeps everything in harmonious balance. Each planet, with its unique mass and orbit, exerts a gravitational pull on the others, creating a dynamic system where every movement affects the whole. This delicate balance of forces ensures that the planets maintain their orbits, preventing collisions and keeping the solar system stable over vast stretches of time. Jupiter, the largest planet in our solar system, plays a particularly significant role in this cosmic dance. Its immense gravity influences the orbits of the other planets, especially those of the smaller, rocky worlds closer to the Sun. This gravitational influence extends even to the asteroid belt, a region of rocky debris that lies between Mars and Jupiter. The presence of Jupiter has prevented these asteroids from coalescing into a planet, instead keeping them in a loose, scattered arrangement. Saturn, with its stunning rings and numerous moons, also contributes to the gravitational interplay that shapes the solar system. Its moons, each orbiting the planet in a precise path, are held in place by Saturn's gravity, creating a miniature version of the solar system within its own orbit. These moons in turn influence the rings, shepherding them and maintaining their structure over time. Further out, Uranus and Neptune continue their slow orbits, their icy compositions hinting at the cold, distant regions of the solar system where they reside. These planets, too, are part of the gravitational dance, their movements influencing not just each other, but also the trajectories of distant comets and icy bodies in the Kuiper Belt, a vast region beyond Neptune filled with ancient remnants from the formation of the solar system. The gravitational forces at play in the solar system are a reminder of the interconnectedness of all things in the universe. No planet moves in isolation. Each is part of a larger system, where the actions of one influence the paths of the others. This interconnectedness extends beyond our solar system, as the Sun itself is part of a larger dance within the Milky Way galaxy, orbiting the galactic center along with billions of other stars. This cosmic dance, both within our solar system and beyond, is a testament to the orderly nature of the universe. The same laws of physics that govern the movement of the planets also apply to the stars, galaxies, and even the largest structures in the cosmos. It is a dance that has been ongoing for billions of years and will continue for billions more, a serene and unending rhythm that connects all of creation. As we contemplate the dance of the planets, we are reminded of the vastness of the universe and our place within it. The silent, steady motion of the planets, guided by the invisible hand of gravity, is a symbol of the order and harmony that underlies all things. In the silent expanse of the cosmos, the universe is constantly growing, its galaxies drifting ever further apart in a gradual and almost imperceptible expansion. This process, which began with the Big Bang nearly 14 billion years ago, continues to this day, with the universe stretching and expanding like a vast cosmic tapestry. The galaxies, which once were tightly clustered together, now float apart in the darkness, each one moving away from the others in a quiet, unending journey through space. This expansion of the universe is one of the most profound and mysterious phenomena in all of cosmology. It is a process that has been unfolding since the very beginning of time, and it shows no signs of slowing down. As the universe expands, the distances between galaxies grow, and the fabric of space itself stretches, carrying the galaxies along with it. This is not a violent or chaotic process, but rather a gentle, steady unfolding of the universe's potential. A quiet expansion that continues to shape the cosmos in ways we are only beginning to understand. The idea of an expanding universe was first proposed in the early 20th century, when astronomers observed that distant galaxies were moving away from us, with the speed of their recession increasing with distance. This observation led to the formulation of Hubble's law, which states that the velocity at which a galaxy moves away from us is directly proportional to its distance from us. This was a revolutionary idea, one that fundamentally changed our understanding of the universe and our place within it. The expansion of the universe is driven by a mysterious force known as dark energy, a force that permeates all of space and acts as a kind of anti-gravity, pushing galaxies apart. Dark energy is one of the great mysteries of modern cosmology, an invisible force that we cannot see or touch, but whose effects are evident in the accelerating expansion of the universe. It is a force that dominates the cosmos, shaping its evolution and determining its ultimate fate. As we look out into the night sky, the light from distant galaxies has traveled millions or even billions of years to reach us. This light carries with it the story of the universe's expansion, a story that is written in the shifting wavelengths of the galaxy's spectra. The further away a galaxy is, the more its light is redshifted, stretched by the expansion of space itself. This redshift is a direct measure of the universe's expansion, a silent testimony to the ongoing growth of the cosmos. The expanding universe is a reminder of the vastness and dynamism of the cosmos, a universe that is constantly in motion, constantly changing, and constantly evolving. It is a universe that is still growing, still unfolding, and still full of mysteries waiting to be uncovered. As we continue to explore the cosmos, we are reminded that the universe is not a static place, but a living, breathing entity, one that is expanding and evolving in ways that we are only just beginning to understand. As the universe expands, the forces that drive its growth remain a subject of intense study and speculation. Central to this cosmic expansion is the concept of dark energy, a mysterious force that makes up about 70% of the universe and drives the accelerated expansion of space. Unlike gravity, which pulls objects together, dark energy pushes them apart, and its effects become more pronounced as the universe grows older and larger. The discovery of dark energy in the late 20th century was one of the most surprising findings in modern cosmology. Astronomers had expected that the expansion of the universe might slow down over time due to the gravitational pull of galaxies on each other. Instead, observations showed that the expansion is actually speeding up, suggesting that a repulsive force is at work. This force, now known as dark energy, is causing the fabric of space to stretch at an ever-increasing rate. Dark energy is not well understood, and its nature remains one of the greatest mysteries in science. Some theories suggest that it could be a property of space itself, a kind of energy inherent in the very fabric of the universe. Others propose that it might be related to a new, undiscovered field or particle. Whatever its origin, dark energy plays a crucial role in shaping the destiny of the universe. As galaxies move further apart, the universe becomes increasingly vast and empty. The stars within galaxies burn through their fuel, eventually fading into darkness, while the space between galaxies continues to grow. Over billions of years, the universe may reach a state where galaxies are so far apart that they are no longer visible to each other, isolated in the cold, dark void of space. This distant future, where the universe continues to expand but with ever-decreasing density, is sometimes referred to as the Big Freeze. The concept of the Big Freeze is just one possible scenario for the future of the universe. Another possibility is the Big Rip, where the expansion becomes so extreme that it tears apart galaxies, stars, and even atomic structures. This would occur if dark energy's influence continues to grow unchecked, leading to a catastrophic end of the universe as we know it. Despite the uncertainties about the ultimate fate of the universe, the ongoing expansion remains a central feature of cosmology. It is a reminder that the universe is dynamic, ever-changing, and full of surprises. The forces that drive its growth are still not fully understood, and the study of dark energy and the expansion of the universe continues to be a major focus of research. As we look ahead to the distant future of the universe, we enter a realm of speculation and theory, where the ultimate fate of all things is considered. The universe, which has been expanding since its birth in the Big Bang, will continue to evolve over billions of years, its future shaped by the forces that govern its growth and change. One of the most likely scenarios for the universe's future is the gradual cooling and dimming of the stars. Over time, the stars that light up the galaxies will exhaust their nuclear fuel, eventually fading into white dwarfs, neutron stars, or black holes. As these stellar remnants cool and lose their brightness, the galaxies will become darker, with fewer and fewer stars shining in the night sky. This slow cooling of the universe, sometimes referred to as the heat death, will see the gradual disappearance of the light and warmth that have defined the cosmos for billions of years. As the universe continues to expand, the distances between galaxies will grow ever larger. Galaxies that are currently visible to us will eventually move beyond our observable horizon, disappearing from view as the expansion of space stretches the fabric of the cosmos. In this distant future, the night sky may appear almost empty, with only the closest galaxies still visible, isolated in the vast darkness of space. In addition to the cooling of the stars and the expansion of the universe, the cosmic background radiation, the afterglow of the Big Bang, will continue to fade. This faint, pervasive radiation, which fills all of space, will eventually cool to the point where it becomes undetectable, leaving the universe even colder and darker than before. The universe, once vibrant and full of energy, will gradually settle into a state of quiet and stillness, with little to disturb the tranquility of the vast empty expanse. In this far future, even the most fundamental particles may begin to decay. Protons, which make up the nuclei of atoms, are theorized to have an incredibly long but finite lifespan. Should they eventually decay, the very matter that makes up stars, planets, and life itself would slowly dissolve into a sea of subatomic particles, leaving behind a universe composed mostly of light, neutrinos, and black holes. Black holes, the remnants of massive stars, will play a crucial role in this future universe. Over time, black holes themselves may slowly evaporate through a process known as Hawking radiation. This slow leakage of energy from black holes will cause them to shrink and eventually disappear, leaving behind an even emptier universe. In the farthest reaches of time, the last traces of these once mighty cosmic objects will fade, marking the end of an era. The fate of the universe might culminate in what some theorists call the Big Freeze, where all remaining energy is evenly distributed across an increasingly cold and dark cosmos. In this scenario, no new stars will form, and the remaining ones will have long since burned out. The universe will be a place where entropy, the measure of disorder, reaches its maximum, and no significant structure or life can arise. Another speculative scenario is the Big Rip, where dark energy, the force driving the universe's expansion, grows stronger over time. If this happens, the expansion could accelerate to the point where it tears apart galaxies, stars, and even atoms themselves. This catastrophic end would leave the universe fragmented into countless particles, each infinitely separated from the others, in a final chaotic dissolution. Despite the vast timescales and the seemingly inevitable cooling and darkening of the universe, these processes are part of the natural evolution of the cosmos. The universe has always been in a state of change, from its fiery beginnings to the slow, serene expansion we witness today. The future, though distant and cold, is a continuation of this story, a final chapter in the grand saga of the cosmos. As we ponder the vastness of the universe and the cycles that govern its existence, we are reminded that the cosmos operates on principles of renewal and transformation. The universe, in its infinite complexity, is a system of cycles, birth, growth, decay, and rebirth that mirror the processes we observe on smaller scales. From the life cycles of stars to the orbits of planets, the universe is a testament to the eternal cycle of creation and destruction, a process that has been unfolding since the beginning of time. One of the most profound cycles in the universe is the life cycle of stars. Stars are born from clouds of gas and dust, condensing under the force of gravity to ignite nuclear fusion in their cores. This fusion powers the star, producing the light and heat that sustain life on planets like Earth. But stars, like all things, have a finite lifespan. As they exhaust their nuclear fuel, they undergo transformations, some swelling into red giants before shedding their outer layers, others collapsing into dense neutron stars or black holes. These remnants of once mighty stars eventually contribute to the formation of new stars, continuing the cycle of stellar evolution. The galaxies themselves are part of a larger cycle of cosmic renewal. Galaxies grow through the accumulation of gas and the formation of new stars, but they also experience periods of quiescence where star formation slows and the galaxy enters a phase of relative dormancy. Over time, galaxies can merge, combining their stars, gas, and dust to create new, more massive galaxies. These mergers are part of the ongoing process of cosmic evolution, a cycle that has shaped the structure of the universe from its earliest days. On an even grander scale, the universe itself may be part of an eternal cycle of expansion and contraction. Some theories suggest that the universe could undergo a series of big bangs and big crunches, where it expands from a singular point, grows for billions of years, and then eventually collapses back into a singularity, only to explode again in a new Big Bang. This cyclical model, known as the oscillating universe theory, proposes that the universe is not a one-time event, but part of an infinite series of cosmic rebirths. The idea of an eternal cycle is not just a scientific concept, it is also deeply rooted in many philosophical and spiritual traditions. Across cultures, the concept of cycles, whether they be the cycles of life and death, the changing of the seasons, or the rise and fall of civilizations, reflects a fundamental understanding of the world as a place of constant change and renewal. These cycles offer a sense of continuity and connection, reminding us that even in the face of change and loss, there's always the potential for new beginnings. As we consider the eternal cycle of the universe, we are invited to reflect on our own place within this vast, interconnected system. We too are part of this cycle, our lives intertwined with the larger rhythms of the cosmos. The atoms that make up our bodies were forged in the hearts of ancient stars, and one day they will return to the universe, becoming part of something new. In this way, we are all connected to the eternal cycle of creation and transformation, a cycle that stretches across time and space, linking us to the very fabric of the cosmos. It is a cycle that offers a sense of continuity and a reminder that the universe, in its vastness, is a place of infinite possibilities. Even without the dramatic events of a cosmic bounce, the universe continues to recycle its components in more subtle ways. The remnants of stars that have gone supernova, for example, spread their enriched elements throughout the cosmos, seeding future generations of stars and planets. These elements, which include the building blocks of life, are carried by stellar winds and interstellar dust clouds, eventually coalescing into new solar systems where the cycle of life can begin anew. This idea of cosmic recycling extends to the smallest scales as well. The fundamental particles that make up matter are themselves subject to transformation, interacting and recombining in countless ways over the eons. Even as stars burn out and galaxies drift apart, the basic constituents of the universe remain, ready to be reassembled into new forms, new structures, and new possibilities. The eternal cycle of the universe is a reminder of the resilience and adaptability of the cosmos. It is a process that has been unfolding since the dawn of time, one that has given rise to the rich diversity of structures we see today, from the intricate patterns of galaxies to the complex web of life on Earth. And just as the universe has evolved through countless cycles, so too will it continue to evolve, finding new ways to express its inherent creativity and potential. As we reflect on this cosmic cycle, we are left with a sense of awe and wonder at the interconnectedness of all things. The universe is not a static, unchanging entity, but a dynamic, living system, constantly evolving and renewing itself. In this eternal cycle, we find a profound sense of peace and acceptance, knowing that we are part of something much larger than ourselves, something that will continue long after we are gone. The eternal cycle of the universe is a story of continuity and change, of endings that give rise to new beginnings. It is a story that invites us to see the universe not as a finite, closed system, but as an open, evolving process, full of possibilities and potential. And in this story, we find a sense of connection to the cosmos, a reminder that we are all part of the same vast, interconnected web of existence, a web that stretches across time and space, linking us to the very heart of the universe.